279, limiting reactants and excess components. And I'm going to talk about this concept a little bit more, kind of skip the experiment, talk about it from the text on the backside of the experiment section, and then hopefully do the experiment tomorrow. All right. We'll go back to a very generic expression of a chemical reaction, okay? One that we've seen many times. I'm just going to use the letters A, B, C, and so on to represent different elements. They could be, virtually any element. So there is no element A or B. But if I were to write on the board A plus B reacts to produce AB. Hopefully this is just a basic formation reaction, right?
Yes.
Never mind. So AB, A and B combine to produce AB. If I were then to come back and say, what if I had 2A and 2B? We'll say that this is a balanced reaction equation, okay? So 1A and 1B produce 1AB. If I said I had 2A and 2B, what would you anticipate the product of the reactions to be?
2 and 2B.
Right. 2AB, right? Now, it may have just almost been intuitive to you, but hopefully you see that all I've done here is multiplied every single stoichiometric coefficient by a factor of 2. Right? So if I had 2A's and 2B's, I would expect them to react to produce 2 AB molecules. Why? Because the base balanced reaction equation is A plus B produces molecule AB. Now we're going to get into this idea of limiting reactants and excess reactants. If I were to tell you that you were in the lab and you had 2A and you reacted that with 1B, what would you produce? Because you know, in truth, that when you have 1A, it reacts with 1B to produce 1 AB molecule, right? So what's happening here, reaction-wise, not quantity-wise, reaction-wise, what's happening here that's any different than what's happening here? Reaction-wise, is anything different happening? Yes, sir.
Once you have an A left up.
Very good. If 1A and 1B combine to form 1AB, then if I have 2A's rather than 1 and a 1B, I will get on the back side AB plus A. Because an A and a B will always combine to form an AB. What's going to happen here is an A is going to combine with a B to form an AB, and then another A is going to form with a B to form an AB. You see what I'm saying? The A's and B's are always going to come together to form the same molecule that they would have formed up here. However, I'm eventually going to run out of B. Rather than using ones, well, if we keep it simple, just 1. If I have 1 and 1 combines to make 1. If I have 2 and 1, what's going to happen? One of these and one of these are going to combine to produce this, and I'm going to be left with 1 extra A. That same principle is behind this idea of limiting reactants. So limiting reactant, you can see the definition on 281. The limiting reactant limits the amount of product that can be formed in a chemical reaction. Okay. So if this reaction engine, what I refer to it as, if the reaction engine is taking place, and when this reaction engine is making molecule AB, by taking 1A and 1B and gluing them together, that's not happening, but let's just use that kind of a Saturday morning cartoon, but that's what cartoons used to be on. I know they're 24 hours a day now, but that idea that I take 1A, I glue it to 1B, I produce an AB, and I send it down the assembly line. So I'm pulling an A and a B, think of it maybe as 2 different colored Legos. I pull an A and a B, stick them together, go. A, B, stick them together, go. A, B, stick them together, go. And I keep producing until what happens? I run out of one of them. If I run out of one block, I can't make any more molecules. If I run out of the other block, I can't make any more molecules. So as I'm in this production line, taking an A and a B, combine it, send it down. A, B, combine it, send it down. At some point, I'm going to reach into the bin for the A's or the B's, and it's going to be empty. If I reach into the A bin, it's empty, I can't combine it with my extra B's. And if I reach into the B bin and it's empty, I can't combine it with all these extra A's I have. I'm done. So what have I done? I've combined all of these individuals to make molecules, and when I stop making those molecules, I'm left with a bin of one or the other. Because if I had both, I'd still be making them. Whatever I have left over is my excess reactants. But we're going to run out of one of them first. This is a simple two-reactant equation. You could have multiple reactants, okay? It's 5, 6, 7, 8 reactants, whatever it is. And I'm making these molecules and sending them down the assembly line, but eventually I'm going to run out of one of them. And as soon as I run out of one of them, I can no longer make the molecule that I'm supposed to be making. And so I run out of one, and then I have excess of everything else. Does that simple analogy make sense to you? I'm pulling from part spins, and no matter what I'm making, if I'm making wagons, and I have, the frame, and I've got the wheels, I've got the pull, I've got all these different parts. As I'm on the assembly line making whatever product, I'm taking the pieces and combining them to make the whole. At some point, something's going to run out. And when I run out, I better stop, because if I don't, I have defective molecules going down, defective products going down the assembly line. I have to stop. I can no longer make what I'm supposed to make. The balanced chemical equation tells you what you're supposed to be making. If, in reality, we have this is our balanced equation, this is our reality. We have, in this case, we have twice as many A's as we need for every B. So eventually, we're going to run out of B, and we're going to have extra A. So when my production line shuts down because I can't make anymore, I'm going to have produced ABs, and I'm going to have a bin of A left over, because the B has all been used up. So that which you run out of is the limiting reactant, and when you hit that limiting reactant, when it goes to zero, everything stops. So you've got a limiting reactant, and everything else is excess. Make sense? If I told you that you were going to make ABs, and I told you had a certain number of Bs, and you had twice as many A's, but you only needed them in a 1-to-1, right? You would say, okay, how many can I make? I can make as many as my B's will allow me. Why? Because I'm going to have leftover A's. It doesn't matter. You could keep coming. I need more parts. Give me more A. I need more parts. Give me more A. I need more parts. You give me more A. Eventually, I'm going to run out of B. If you keep giving me what I already have too much of, it's not going to change how many I can make. I'm going to have to stop when I run out of one of them. And that's exactly what's happening with this idea of a chemical limiting reactant. In a chemical process, if you have the balanced equation, and this is where we're going from a formula to what's actually happening in the lab. If I'm in the lab, and we'll see this tomorrow with the different pieces, I can have two things that react, and I can mix them. And if the reaction perfectly takes place, if I have exactly the same numbers of A's and B's, I'm going to produce molecule AB. If I've used up all of it and I go ahead and just add more B, what's going to happen? Is there any A left to work? No. I add more B, nothing happens. I add more B, nothing happens. I add more B, nothing happens. I keep adding, and all I'm doing is throwing extra content into this, but it's not reacting because it doesn't have its reactive partner here. It doesn't have the other reactant that it needs. Now, if I've got all this excess B, and I suddenly come around and give it a little dose of A, okay, I have way too much B, I give it a shot of A, A's and B's are going to start producing these molecules until one of them runs out. And then it's going to stop. You're going to have leftover one or the other. Whichever you had too much of, you're going to have that in your container. Okay. One of the beautiful things about this, one of the powerful things about this, is in any reaction, once you have the balanced reaction equation, and the balanced reaction equation, I know other years I've referred to it this way, is your perfect recipe. And I think I've referred to it in here as that as well. A balanced reaction equation is your perfect recipe. I mentioned before, the recipe kind of falls apart because if you're making, I think they generally say brownies. If you're making brownies and you forget how many eggs you put in one too many eggs, it just ruins the brownies, right? It makes it taste different. I think, an extra egg makes it cakier or something like that, okay? But in a chemical reaction, think of it this way. If you had a perfect brownie mix and you added one too many of the ingredients, what would come out of the oven at the end is your perfect brownies, and then whatever you get too much of on its own. It's like if you put an extra egg in the brownie mix, what would come out of the oven is a brownies and with an egg on top, you know? Because it's not going to take that extra ingredient. It's not going to use it. It's kind of there where God in chemistry has kind of set it up. If we're going to make what we're supposed to make, if you put too much of something in, we're going to give it back to you at the end, on the other side. That's the case here, where if I put too much of one of the ingredients in this case too much A, it's going to make what it's supposed to make. It's going to make the brownies. And it's going to kick back whatever extra you gave it, because it doesn't need it. It's not going to use it. So you can't mess up the molecule. That's one of the things I hope you're starting to understand is just because you add something different in the lab doesn't mean you can produce something different. I mean, I mix A and B, it's going to make AB. It's not waiting for me to get the perfect mix. If I do two A's, nature is not required. God does not require it to use up everything that I give it. It's just basically saying, I'm a production engine. I'm going to make ABs. You give me too much of something, I'm not going to use it. It's going to stay there. Tomorrow we're going to see that if you add too much of something that's, say, a solid, and it goes into this reaction, if you got too much solid, when you're done, what are you going to have? You're going to have leftover solid. And if I put too much liquid in, at the end of it, I'm going to have excess liquid. But if I do it in perfect proportions, it's going to create a perfect reaction that's not going to have any excess components of anything. Now that's difficult to get to because when we start using the mole concept, remember it's times 10 to the 23rd pieces, and so I would say it's impossible, maybe virtually impossible, to get exactly the right pairings. You're going to have excess of something, but it's going to be so infinitesimally small in most cases that it's not an issue. But if you know what is your limiting reactant, you know what component is going to run out. And if you know what component is going to run out, you know how much of everything else is going to be used and produced. Okay. If I said in this case that I have, let me erase this just so we have the concept now. I'm going to go back to my basic A plus B produces AB. And if I told you that I have 10 A and I have 15 B, shouldn't write it like a chemical equation. I tell you that I have 10 A's and 15 B's, and they react to produce according to this balanced reaction equation. This is the theory. This is actually in the lab. I'm told 1 plus 1 produces 1. I say, okay, I mix them together and I find out later what I did was I mixed 10 and 5 and 15. What is going to be the product of this reaction?
It would be 10AB plus 5.
Yep. 10AB plus 5 what?
B.
Plus 5B. Right. Let's balance the equation. A's, 10. A's, 10. B's, 15. B's, 10 plus 5 is 15. See? It's a balanced equation. We have the same number of each of the elements on both sides. And they produce AB in a 1-to-1 relationship. 1-to-1 produces 1. So 1-to-1 produces 1. That reaction is going to run its course until it runs out of something. Now, what did it run out of? What is the limiting reactant in this statement here? A. A is going to run out. So A runs out means I'm going to have excess of everything else. In this case, I have excess B because A ran out. A runs out means that on the product side, I'm not going to find anywhere where A appears alone in its elemental form. I'm not going to have a plus 2A. Why? Well, those two A's would have combined with two of these B's to produce two more ABs and leave three B's left over. There's not going to be excess of everything. There may be excess of all but one. Something runs out and stops the engine. Okay. So, 10 plus 15 produces 10 plus 5. If I told you that I have 5A if I told you that I had 5A and some quantity of B that I reacted to produce 5AB, how many B must I have? Must have 5, right? If I'm doing a reaction and I know that it's going to be a 1-to-1, and I tell you that I react A with excess B. Now that phrase excess, what that means is if you have excess of something, it's not going to run out. You got plenty. Okay. So one code word in chemistry for them to tell you that your limiting reactant would be A is to say that you react A with excess B. Excess B means it's not going to run out in your reaction. It's not the limiting reactant, which means in this case A must be. Okay. So oftentimes they'll give us a statement like, for example, if I react 15A and excess B. Well, if I'm told I have excess B, that's going to tell me in my product side that I'm going to have some amount of B left over. Why? It's excess on the reactant side. If it's excess on the reactant side, it doesn't run out, which means I'm going to have some left over after the reaction's over. Okay? Now, you're not always concerned necessarily when you do the actual reaction of how much B is left over. You can compute it, but that may not be your concern. Your concern may be, okay, I have some quantity of A in excess B, and I want to produce 15 AB, knowing that I'm going to have excess B. See that? I have A's and B's to produce 15 A's and B's. I have excess B, which means I'm going to have B left over, means A is my limiting reactant. A is the one I have to nail. It's got to be correct, because it's running out to form this. How many A's do I need to make 15 ABs? I need 15 of them. If I react 15 A's with an excess of B's, it'll make 15 ABs and leave me excess B left over. So those are the terms: limiting reactant, what is going to run out; excess reactants, what you got plenty of; and then the balanced equation, which gives you what you can forecast the product is going to be of the reaction. All right. Now let's go ahead and put some real chemistry around this. On page 282, let's use this concept with the reaction they show for fully analyzing chemical equations on the top of 282. Let's take a look at this reaction real quick. Magnesium solid reacts with hydrochloric acid aqueous to produce magnesium chloride aqueous and hydrogen gas. I would always encourage you to take a moment and just visualize what this looks like. Okay? What does this reaction look like? I've got a solid and an aqueous. If it says a solid, it could be various forms. I want you to just think in terms of like a salt shaker. Whatever this is, it's in solid chunks of some size. So think of it as a salt shaker full of magnesium, solid. Into aqueous, what does that mean? In water. So I've got hydrochloric acid, HCl, in water. It's diluted. It's not pure HCl. I've got water with some hydrochloric acid in it, so it's diluted to a certain, molarity there. So I have hydrochloric acid in water, and I add to it solid magnesium. I've got a beaker, or let's say of hydrochloric acid diluted, and a salt shaker of magnesium. I'm adding magnesium into this aqueous solution that includes hydrochloric acid. These react to produce magnesium chloride, aqueous. Okay. Now the aqueous again means in water. It means it's dissolved into the water. So I have a solid and a liquid that produces a liquid and a gas. What has happened to the solid? As you're taking the solid and shaking it into the liquid, it's reacting and dissolving, it's disappearing, right? So I've got in terms of phase, I have a solid and liquid that, as I drop it in there, it turns into a liquid and a gas comes off, a hydrogen gas. And you look at your neighbor and say, put out your cigarette. Why? Boom! Because he's going to blow up the hydrogen. Okay? So I took a solid and a liquid, technically a solid and an aqueous, to produce an aqueous and a gas. So looking at this is, let's say this is the balanced reaction equation. Okay? If I look at this and I say, I need one of these and two of these to produce one of these and one of these. Are we good with that? One atom of magnesium and two molecules of hydrochloric acid react to produce one molecule of magnesium chloride and one hydrogen molecule. Now what if I said I had 1/2 and 1? What would we produce? Do you see that these are in the same proportion? I've just taken this and I multiplied it by 1/2. So if I have half as much of this and half as much of this, I'm going to produce half as much of this and half as much of this, right? So we've taken the standard reaction equation and we've multiplied the stoichiometric coefficients by 1/2. So if I have a 1/2 and a 1, I produce a 1/2 and a 1/2. But what happens if I come in here and say I have 1/2 and 2? Okay. I have half a mole of magnesium and I have 2 moles of hydrochloric acid. What am I going to produce? Okay. What runs out? Which of my reactants here is the limiting reactant? Pardon? Magnesium, right? If it compares 1 to 2, and I have 1/2 to 2, you see that this is being limited? I'm going to run out of this, and I'm going to have excess of this. Now, how much of this is going to be used up? When I do it perfectly, a 1/2 requires a 1, right? So this 1/2 is going to require one of these. For the reaction, only one of them is going to be used, right? What's my product going to be? My product is going to be the reaction, as many reactions as I can sustain. A 1/2 and 2, well, if we know it reacts a 1/2 and 1 produces a 1/2 and a 1/2, then a 1/2 and 2 produces a 1/2 and 1/2. Why? Because I've got the same amount of my limiting reactant. Here it runs out perfectly. Here it runs out, and it runs out with excess. How much do I produce? As much as the perfect recipe would support with that much of my limiting reactant. I only have enough magnesiums to match with hydrochloric acids as will consume the 1/2 mole. That 1/2 mole is going to consume 1 mole here. And so I'm going to have a 1/2 and a 1/2, and then what else? Plus 1 HCl aqueous. Why? I've used up all my magnesium. I have not used up 1 mole of my hydrochloric acid. So on the back side, I've got the reaction as if I had only used a half to the perfect recipe. And then whatever I did not use up is in excess. If I take these amounts and I combine them, and this is the product of my reaction, and I have hydrochloric acid left over, if I take that beaker and I add more hydrochloric acid, what's going to happen? No, nothing is going to happen, because hydrochloric acid is already in excess. If I add more of what I already have too much of, nothing else happens. That's like putting more of the part I have in the bin and not giving me what I'm out of. But if rather than adding more hydrochloric acid, I add more magnesium, shake, 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 shake. Well, now that new magnesium is going to react with this excess to produce more of this product. And if I add exactly as much as I need at the backside, let's say we did the reaction, and after we did it, we realized we cut it short. Oh, I didn't put enough magnesium to fully react with this. How much should I have put in? I should have put in a whole mole. I only put in a half a mole. Let me add another half a mole. That other half a mole of magnesium would react with this whole mole of hydrochloric acid, and we would produce 1 and 1. Okay? Let's look at example 8.2 to put real numbers to this again. If you need to break it down, put it this way, if you're already saying this is way too hard, that's like standing at the tee and saying the bat's too heavy, okay? You can do this, Junior. Let's just go. Keep going. You can do this. Example 8.2, they walk you through the whole thing, but let me write it on the board. Calcium carbonate plus 2 hydrochloric acid reacts to produce calcium chloride, water, and carbon dioxide gas. Okay. So again, visualize the phases with me, if you will. I have hydrochloric acid in aqueous solution. I have a liquid in this beaker. And I have solid calcium carbonate. I'm shaking calcium carbonating. That's the antacid. That's Tums. Boom, 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 shaking in there. Why? In your stomach, when you have heartburn, when you have that pain in your stomach, that's the acid eating at the lining. You've got too much acid. We need to neutralize that acid. This is the acid in your stomach. This is the Tums you take to neutralize it. This will make more sense later when we do acid-base reactions. But here's the basic reaction. I've got Tums. I take it so it can react with the acid in my stomach. And what's it going to make? It's going to make calcium chloride. It's going to take that acid that's burning your stomach. By adding Tums to it, it's going to convert it into carbon dioxide gas, water, and calcium chloride. That's why they say take Tums for your bones. Sometimes you get encouraged to take antacids for your bone health. It's because the calcium in here will help your bones. Water is benign. It basically, when it turns to water, it then dilutes whatever acid is still there. And then you have the carbon dioxide gas. You burp. Get rid of the gas because you've got gas in your stomach now. And on this side of your intestines, that means a burp. On the other side, we get the reaction we had earlier in the class. Okay? So this is the reaction that they're talking about in this example. And they say if 0.0075 moles, 0.0075 moles of calcium carbonate, then how many moles of hydrochloric acid are needed? Now, what I'm doing here is I wrote my balanced reaction equation, and I'm looking at calcium carbonate and hydrochloric acid. I know that I'm going to do something with stoichiometry that involves those two molecules. And so I automatically, by habit, go through and I draw a vertical line underneath the stoichiometric coefficients for the two molecules that are in question. Okay? And the question then is, how many moles of hydrochloric acid can neutralize? How many moles of hydrochloric acid can this many moles of calcium carbonate neutralize? So when it says this, I'm trying to look for, in the perfect reaction, if I have this much, how much of this will it combine with? How much of this will it react with? Another way to think of it is, how much of this in your stomach will it get rid of by converting it into this? Okay? So stoichiometrically, I'm looking at calcium carbonate and hydrochloric acid. How much? Now hopefully you see from what we did yesterday that this is basically, if I were to take this and blow it up, actually let me just rewrite this, it's going to be easier. Remember I said it's this one and it's related to this one. Okay? What is my relationship?
1 to 2.
Good, 1 to 2. Where do I get that from? The 1 and the 2. My relationship is 1 to 2. I've been told that I've been given 0.0075 moles of calcium carbonate. Remember, this line below this area down here, this is for moles. You should reserve that for moles. So I've been told that I have this many moles, and I've been asked how many moles of this will it neutralize, hydrochloric acid. My process then is taking me from here to here, right? This is the direction of my question. From my given to my unknown. How much of this hydrochloric acid will react with this much calcium carbonate? What's my conversion factor? As I move from here in this direction, which number do I hit first? 1. So I drive it under, and my conversion factor becomes 2 to 1. Right? So, pardon? Right, 2. 2 over 1 is 2. But I always try to put it in a fraction so you can recognize that you did the mechanical movement of the 1 was driven under the 2 to form a conversion factor of 2 over 1. It's not always going to be a 1. It could be a 2 over 7. It could be other coefficients. So I just, by practice, always put it as a fraction. So 0.0075 or 0.0075 moles of calcium carbonate can neutralize how many moles of hydrochloric acid? 2 times that much. It can neutralize 0.015 moles. See? 0.0075 moles of calcium carbonate reacts with, in the perfect stoichiometric equation, right? Perfect balanced reaction equation. It will neutralize twice as many moles of itself in this. Now, the next part of it says, when it neutralizes that amount of stomach acid, how much calcium chloride, H2O, and carbon dioxide are formed? How much of all of those are formed? How many moles of each? Okay, now you could go through and go, okay, well, down here, up to here, I've got this much reacts with 0.015 times 2 to 1, that makes it 1/2 and brings it down to 0.0075 again. You can just walk those numbers, do that same process all the way across the board. Make sure you do the math right, make sure you do your setup right, all that kind of stuff. Or you could stop and say, well, wait a minute. What's the shortcut here? I know you see it. What's the shortcut here? What's the relationship between this and this? 2 to 1. This and this? 2 to 1. This and this? 2 to 1. So you can see they're all going to be the same thing, right? They're all going to be, whatever this is, it's going to be the same for all 3 of them. What's the relationship between this and this? 1 to 1. What does 1 to 1 mean? Same amount. For every one of these, I'll produce one of these. So if I have this much, it's going to produce that same amount. 1 to 1. 1 to 1. 1 to 1. Same. So, if 0.0075 moles is used in this reaction, then 0.0075 moles of each one of those is produced. Why? They're related to this reactant in a 1-to-1 relationship. Now, if you did it the long way, you could, like I just described earlier, let's say that we're doing this. Okay, this comes down 0.015 moles. I go across here, how much calcium carbonate is being produced? Well, my stoichiometric coefficients are 2 to 1. When I move from this way to this way, I multiply by 1/2, and I'm going to get 0.0075. If you want to just keep walking it across, I could do this then. If this is now 0.0075, hopefully here you'd see that from here to here, what's the relationship? 1 to 1. So it would be this again, 0.0075. Okay, from here to here, what's the relationship? 1 to 1, which means 0.0075. See, you can walk all the way through. Once you have one of them, you can figure out, for the perfect balanced reaction, what you have for all of them. Now, let's say we don't know exactly how much S is in there, so we like take 17 tums, whatever it is, okay? When we take that much tums, we can assume that we're going to have excess calcium carbonate, which means we're going to neutralize all this acid, and we're going to have excess calcium carbonate somewhere on the other side. But when this reaction actually takes place and says that this is how much we have, how much can it neutralize, that assumes you're going to have excess hydrochloric acid, which means this thing here is dictating the whole reaction, how much is produced, because this is going to run out first. And since it's a 1 to 1, that amount, it's all the same amount. Okay. We have about 10 minutes left. I encourage you to go through now. Let's go ahead and, on your own, work on your own 8.2. If we want, I can put the answer to 8.2 up on the board. Obviously, it's in your book as well. At this point, you should be able to answer review questions 1, 2, and 3, practice problems 1 and probably 2. Okay? Those later ones might be pushing where you're at in your understanding right now, but take a look at review questions 1, 2, and 3, practice problems 1 and 2, and we're not yet to what you need for extra practice problem number 1. If you want to do more work on this, I'm going to do 8.2 on the board. Do it on your own, into your own notes. Don't look up here and see what I've done until you're ready to compare what you've done and look yourself critically. Remember, it's always easy to think you know it when you look up on the board and get hints all along the way. So don't do that. What I'm going to do is answer 8.2 in the way that I've taught you. The book uses the conversion factor method, which is equally as valid. Matter of fact, what I do, remember, comes from that. So if you do it simply by doing conversion factors, that's awesome. Use the visual to just back up your conversion factor. Look at for just a minute. I solved this two different ways using two different relationships. The first time I did it, I answered the first part by saying I'm relating the iron ore to the oxygen that's represented by this solution set right here. And then I figured out the iron oxide by taking what I computed here and using the 11 to 2 relationship to solve for iron oxide. It's equally valid, it's just as true to start back where you started from here and relate the iron ore all the way over to the iron oxide. Because here you're multiplying this by 11 times over 4, and you're multiplying here by 2 over 11. Do you see that 11 over 4 times 2 over 11 is going to be 22 over 44, which is 1/2? So down here, its multiple is 1/2. The math works both ways. So you can always relate a known to an unknown if you have a balanced reaction equation and relate the stoichiometric coefficients. Clear as mud, Austin?
Yes, sir. I was just sitting down.
Mm-hmm.
No problem.
Good thing your word is good, huh? Any questions for me? We only have a couple minutes left. Tomorrow we're going to hopefully do the lab, which will reinforce this idea, what it is we're looking at. Specifically reinforce the idea of excess reactants and the reaction engine stopping when not everything is used up. There's leftovers. Yeah, so what we're going to do is take plastic bottles with vinegar in them and balloons hooked to the top that have baking soda in it. We're going to tip the balloon up to drop the baking soda into the vinegar. And when it reacts, hopefully, yeah. And when that reacts, it's going to produce a certain amount of gas. So if we have the same amount, with the same balloons, it should produce the same. But if we're going to find out that if we have too much vinegar or too much baking soda, it's still only going to produce the same amount of gas. So if we have too little, let's say we think of vinegar as our baseline. If we have too much baking soda in one reaction and too little baking soda in the other reaction, and close to the perfect amount in the middle reaction, right? The one where you've got too little, it should produce less. The one where you have the perfect amount should produce a certain amount more. And when you have excess, it should not produce any more. It should produce the same amount of gas. Should. If we do our measurements right.